average acceleration vector. So this should be the velocity vector. Which of these vectors shows the position vector, velocity vector, and the acceleration vector? So in the last video, we discussed about the position vector, displacement vector, velocity vector. Now in this video, our focus would be on the average acceleration vector. And mathematically we write that average acceleration vector is equals to the change in velocity over the elapsed time delta t. So let's understand this average acceleration vector by taking this example. So we have this coordinate system. This is positive x, this is positive y, and suppose that a particle is traveling along this curve, something like that. Now let's consider 2 points on this curve. Let this be point 1 and let this be the point 2. Now the velocity vector at point 1 is represented by this this arrow. This would represent its velocity vector. Let it be v1. And similarly at point 2, this would be v2 vector. Now delta v. So delta v, we know it is the final velocity vector minus the initial velocity vector, and in this case we have v2, which is final velocity. So v2 vector minus the v1. Or we can write that v2 vector is equals to v1 plus delta v. Now let us try to represent this delta v onto this figure, and for that what I'm doing is I'm just copying this figure and then paste it. So this is copy and then I'm just pasting it here. Now to represent this delta v on the figure, what I'm doing is I'm just taking this vector v2 and I'm putting it here. I have not changed its direction, I have not changed its magnitude, I have just changed its position, which we can do for a vector. So this is v2 here. Now delta v. Now for delta v, we have to join the head of v1 to the head of v2. So let me represent on the figure. So this would represent our delta v vector. So this is delta v. Now could you guess the direction for the average acceleration vector? This one. So the direction would be parallel to the direction of delta v. It's the same thing that we did to find the direction for delta r, the displacement vector, in the last video. If you haven't seen the video, click on the bell icon to see that video. So this is the direction for average acceleration vector. Now one question for all of you. Could a body accelerate with constant speed? So pause the video and think. Now the answer is yes, it is possible. Let us understand this concept with this example. So we have this car traveling on a circular track with constant speed. Now here the direction of the car is changing at every instant, so the velocity is changing with time, and thus we can say that the body is accelerating. So the answer is yes, it is possible. Now suppose that we can take the initial velocity for the car is vi, which is 12 meter per second, and it's along the x direction, so x cap, the unit vector. Now in this direction we have vf. Let this be the final velocity vf. It is equals to, magnitude remains the same but the direction changes, so this is y cap. It's along the negative y direction. Now average acceleration, we just studied that it is equals to vf vector minus the vi vector divided by the elapsed time delta t. Now the time taken by the car to reach from this position to this position, let it be delta t, which we can take to be say 10 seconds. Now the average acceleration, so this would be, we can put the values now to find the average acceleration. So final vector we have this is minus 12 meter per second. This is y cap. minus 12 meter per second, and this would be x cap. I'm writing x cap here. Divide by delta t is 10 seconds. On further solving, we'll get this value to be minus 1.2 meter per second squared x cap and minus 1.2 meter per second squared y cap. So this would be the average acceleration. Now we wish to find the direction for the average acceleration. So what I'm doing is I'm taking this vector vf and I'm putting it here. So copy and then paste. So I'm taking it here. Now delta v would be represented by this vector. We have just joined the head of vi to the head of vf. So this red arrow represents the change in velocity vector delta v, and we studied just now that the average acceleration vector will be parallel to this vector. So this would be our direction for the average acceleration. Thus we can conclude that the average acceleration is in the direction of delta v, which is towards the center of the circle. So there are few points that you should remember about the velocity vector and the acceleration vector. So the velocity vector always points in the direction of particles motion, and this is a very important point. Let me write here. Now in one dimension, the acceleration is either in the same direction as that of velocity or in the opposite direction, but in two dimension the acceleration can be in any direction relative to velocity, and the acceleration vector can point in a direction other than the direction of motion. So let me write this point, very important point. Now with these points in mind, let's discuss one thing. So suppose a particle is moving along this blue curve, and we have considered 4 points, point 1, point 2, point 3 and point 4, and there are two vectors drawn at every point. Now one of them is a velocity vector and other is an acceleration vector. So pause the video and try to figure out which vector shows the velocity vector and the acceleration vector. So I hope you tried. Now let's discuss. Now we studied that the velocity vector always points in the direction of motion. So here the particle is traveling like this. So this should be the velocity vector and this should be the acceleration vector. Similarly at point 2 the particle is traveling like this. So at point 2 this should be the velocity vector and this will be the acceleration vector. Similarly at point 3 this would be the velocity vector, this is acceleration vector, this is velocity vector and this is acceleration vector. Now at point 1 the particle is slowing down, that is why the acceleration is opposite to the velocity, and at point 4 the particle is speeding up, that is why the acceleration and the velocity is in the same direction. Now at point 2 and 3 the particle is taking a turn, so that is why this acceleration points towards the center of the circle, and this velocity v is along the motion of the particle. Now let's summarize everything that we studied about the position vector, velocity vector and the acceleration vector. So we have a particle moving along this blue curve, and you have to determine which of these vectors shows the position vector, velocity vector and the acceleration vector. And before attempting this question, please see my previous video so that you can attempt this question easily, and for that you can click on the bell icon. Okay, so I hope you tried. Now this vector will show the position vector of the particle. This is r vector. Now this red vector will show the velocity vector, and this green vector will show the acceleration vector. So this is all with this video, and in the next video we'll discuss the relative motion.